last topic of the PN junction, that is metal semiconductor junction. So metal semiconductor junction, many of the useful properties of a PN junction can be achieved by simply forming an appropriate metal semiconductor contact. This approach is obviously attractive because of its simplicity of fabrication. Because of simplicity of fabrication. Also, metal semiconductor junctions are particularly useful when high-speed rectification is required. So, using PN junction diode, we can rectify the signal. So, that is your rectification. So, when we need to rectify for the high-speed signal, then we consider P metal and semiconductor junction. On the other hand, we also must be able to form non-rectifying contact. Non-rectifying contact, that means it is ohmic contact to semiconductors. So before we discuss about the metal semiconductor junction, we just discuss about some point, that is what is work function. The difference in Fermi energy level and vacuum level is known as work function, which is denoted by phi. The vacuum level is the measure of the energy level. So we know Fermi energy level. What is the vacuum energy or vacuum level? The vacuum level is the measure of the energy level of an electron when it is absolutely free. That is, the electron is outside the metal surface. That level is called the vacuum level. Next point, electron affinity, which is denoted by this sign. This is called chi. This one. So the electron affinity, what is the electron affinity? Now, the difference of energy level between the bottom of the conduction band and the vacuum level is known as the electron affinity of a semiconducting material. Okay, bottom of the conduction band, that means EC energy level, to the vacuum level, that is denoted by the chi, which is called electron affinity. So here we see when phi m is equal to chi, means the work function of the metal, m for metal, with the electron affinity, if it is high, then rectifying contact with n type, then metal with n type make a rectifying contact and metal and p type make a ohmic contact. When it is the low, then metal and n type make a ohmic contact and metal and n type make the rectifying contact. So ohmic contact is nothing but a non-rectifying, and rectifying means in case of forward bias, the current flow, reverse bias, current block like a PN junction diode. That is rectification properties or rectification characteristics. So metal and n type, when this value is low, then it is behave as a rectifying. When metal and n type ohmic contact with behave n is ohmic contact. So we see the metal and semiconductor, the difference is metal is good electrical conductors and semiconductor intermediate conductivity. In case of metal, there is a free electrons. In case of semiconductor, there is a narrow band gap. In case of metal, conduction band and valence band overlapping. In case of semiconductor, either electrons or holes as a majority charge carriers. And Fermi level at center of conduction band and valence band. Fermi level can be shifted either conduction side or valence band side. So this is the difference. Depending on this concept, we draw the energy band diagram for metal and semiconductor. So this is the metal where the Fermi energy level, and above the Fermi energy level Q phi m, which is the vacuum level. So where partially full band and many free electrons in case of metal. Whereas in case of semiconductor, there is a two types of semiconductor, N type and P type. You see, this is the conduction band energy band, this one and this one. This is the valence band, which is the energy is denoted by EV and EC. Above, previously we discussed about it, that the above the conduction band where the electrons are free, absolutely free, that is we call vacuum level, which is denoted by the electron affinity of the semiconductor, that is chi. So total energy is Q into chi. So from the this point to this point, this is the difference between conduction band and valence band by the electron affinity. And also here the work function of the semiconductor in case of N type from the Fermi energy level to the vacuum level, which is denoted by phi s into Q charge, then we get the energy. Similarly, in case of P type, Fermi energy level to the vacuum level, that is Q phi s. So in this case, chi is denoted here electron affinity of the semiconductor. Phi m is the metal work function and phi s is the semiconductor work function. So here, in case of semiconductor, N type and P type, EF in between the band gap, valence band almost full, conduction band almost empty. These are the condition in case of the metal and semiconductor when we discuss about the energy band diagram for those type of materials. So now when we make a junction, that means metal with N, metal with P type semiconductor. So what happened? So before that, again we see that application of the PN junction, metal and semiconductor junction, we already discussed in previous slide. Number one, ohmic contacts to N type and P type regions of semiconductor devices. Okay, because when we in every devices we need to make a contact. So if we see there is a P or N, so there is need to the contact. That should be ohmic, because we need to measure the current of the PN junction. So it's need to be ohmic. So that time we require the metal. So metal and semiconductor junction. So we discuss elaborately about the ohmic contacts. Next slide. And number two, rectifying junction which switch faster than PN junction since majority carrier phenomena dominate. Okay, this is the applications. So where here vacuum level denoted by the E naught, which is reference energy that an electron just free of the material would have in vacuum. And phi s is the work function which is equal to E naught means vacuum level energy minus EF Fermi level energy by Q. Therefore, phi s depends on doping level in semiconductor. Very important point. Therefore, phi s depends on doping level in semiconductor because when we change the doping concentration or concentration of the carriers, electrons and holes, that means the Fermi energy level should be changed. We know when the doping very high concentration of the electron, then Fermi energy level very closer to the conduction band. So it depends on the doping level. Energy required to bring an electron from the Fermi level to the vacuum level, that is the work function phi s. Chi or electron affinity E naught minus EC by Q. Therefore, chi is a property of the material. Chi is the property of the material and does not depend on doping. That means it's a property. It is the fixed for the different material, or there is a finite value. Energy required to bring an electron from the conduction band to the vacuum level, that is your electron affinity. So phi ms is the phi m minus phi s. So that is metal semiconductor work function difference. Metal semiconductor work function difference. So in addition, E naught or vacuum level must be continuous since the energy in the vacuum cannot change abruptly. Repeat, E naught or vacuum level energy must be continuous since the energy in the vacuum cannot change abruptly. Number two, chi and phi m are constant since they are properties of the material. So using these guidelines, the band diagram can be drawn for a metal in contact with a semiconductor where phi m less than phi s, phi m less than phi s. So we see, so phi m less than phi s, when it is happened, that means it is metal, and this is n type for semiconductor. Why n type? Because Fermi energy level closer to the conduction band. So this is the energy band diagram for the metal and semiconductor, where the semiconductor is n type, and where you see phi m less than phi s, that means the distance from the EF in case of metal phi m, and distance from the between the EF and the vacuum level in the semiconductor side is larger than the phi m. Phi s is the larger than the phi m. Okay, when it is happened, then if we draw the energy band diagram, when make a junction, then we can describe the working principle of this junction, or what is the working uh, steps for this junction we can discuss. If we draw the energy band diagram for metal and semiconductor, where semiconductor is n type and also phi m less than phi s. So same procedure. First we draw the Fermi energy level, which is the constant in a system. So this is EF, for the junction, metallurgical junction. So this is metal N type conduction band closer to the Fermi energy level, EC, and valence band below the EF, EV, and vacuum level above the chi or phi s. Here also vacuum level above Fermi energy level, that is phi m. At the metal side, the Fermi energy level is constant or vacuum level also constant, whereas this is your Q phi m is fully occupied. So due to that, at the junction, the conduction band is bent this way, because you see left side metal and right side N type. When it is make a junction, that means the carrier has moved from either side. So then Fermi energy level of the metal is downwards and Fermi energy level of the N side is upwards. So that means if it is upwards, it is downwards. So conduction bands is bent at the junction. So initially here, so now here, initially here, now it is upwards. That means it's fixed here, and there is a bend and it goes at the neutral region. So it is bend here. So vacuum level also bend at this point, where this is the Q chi. So this is the energy band diagram for the metal and semiconductor at the constant of phi m less than phi s. So in this case, what happened? If we apply the forward bias, that means positive and negative. So it is the bend EC is the upper side. So for the electrons, this is the downhill. So electron is easily moved from the N side to the P side. And if it is reverse bias, then also if it is Fermi energy level or if EC conduction band is downwards, due to the higher concentration of electrons from the middle side, it is moved from the this side to the this side. So that means either forward bias and reverse bias, the current flow due to this junction. So this type of junction is called non-rectifying or ohmic contact or ohmic contact. So when we make a metal and n-type semiconductor at the condition of phi m less than phi s, then it is behave as a non-rectifying or ohmic contact. Similarly, in case of metal and p-type semiconductor at the condition of phi m and phi s, what happened? You see phi m is smaller than the phi s. Okay, same. First we draw the Fermi energy level, EF, then metallurgical junction, then valence band, which is closer to the fiber energy level, conduction band above the fiber energy level. This is the metal side is occupied, p-type and metal. So above 5m there is a vacuum level AC. Above chi there is a vacuum level. So again you see this the downwards and this is the upwards. So what happened? The conduction band is bent and valence band also bent. Whereas the vacuum level also bent. So that is your Q chi, that is your Q phi m. So in this case what happened? You see this is the positive for the hole, this one the barrier, this is the barrier. In case of PN junction diode, you just remember that, this is the barrier for electron, whereas this is the barrier for hole. So holes move from semiconductor side to the metal side. For that there is a barrier. So when it is forward bias, then this barrier is decrease, and if it is decreased then the holes move from this side to the this side. If it is reverse bias, then it is again increase, this barrier is increase, so holes cannot move from this side to this side. Same operation like PN junction diode. You always remember PN junction diode concept, same concept here. So when metal and p-type semiconductors make a junction at the condition of phi m less than phi s, then what happened? In case of forward bias, the current flow, and in case of reverse bias, current is blocked here, so it is behaved as a rectifying. So this contact is called rectifying contact. Rectifying contact. So in case of phi m less than phi s, we see that if metal with we make a junction metal with the n type, then it is behave as a ohmic contact, and metal with p type, then it is behave as a rectifying contact. So similarly, if we see phi m greater than phi s, there is another condition, phi m greater than phi s. So if metal and p semiconductor, where you see phi m is larger than the phi s, so what happened with this case? You see, if it is changed, it is downwards and this is upwards, means this is fundamentally here, so that means it is downwards, it is upwards, then it is make a junction. So we make first Fermi energy level for the system when it's make a junction between metal and p-type semiconductor at the condition of phi m greater than phi s. First EF, metallurgical junction. This is a p-type, this is a metal. For p-type, valence band is the closer to the Fermi energy level, conduction band is above Fermi energy level, occupied above vacuum level, above fiber energy level at the metal side, which is very large, Qy phi m, above Ec, that is your Q into chi. So in this case, the energy band is bent this side. This is downwards, this is upwards. So it is fixed. If it is downwards, that means it is bent. So at the junction, this is the bend. So in this case, for a holes, so this is the downhill. So it is easily moved from P side to the metal side and vice versa. So this contact is nothing but a non-rectifying. So you see, when phi m less than phi s and make a junction between metal and n type, then behave as a non-rectifying or ohmic. And when phi m greater than phi s, metal and p type junction is behave as a rectifying, non-rectifying. So in case of phi m greater than phi s, if the junction is created due to the metal and n type semiconductor, then what happened? You see, there is a phi m is larger than the phi s. So this is when it's make a junction, then it is upwards, then it is downwards. So initially we make a junction fiber energy level EF metallurgical junction. Conduction were closer to the fiber energy level and valence were below the fiber energy level. A vacuum level for the metal is above 5, which is filled, whereas vacuum level at the semiconductor side above the EC, that is Q chi. So it is bent this way. This way. So for the electron, this is the barrier. This is the barrier Q phi Bn, and this is called, this distance called denoted by the phi B, which is called Schottky barrier, which is called Schottky barrier, which is called Schottky barrier. So in this case, when it is forward bias, then this distance is decreased. So easily electrons move from this side to this side. If it is reverse bias, then this distance increase and not move from the n side to the p side. So it is behave as a rectification. It is called rectifying contact. So this type of metal and n-type semiconductor at the condition of phi m greater than phi s, which is called rectifying contact. That contact also called the Schottky diode or Schottky barrier, Schottky diode, SCHOTT KOI Schottky diode. This type of diode is called Schottky diode. So due to the Schottky effect, the electrons is move from inside to the p side. So we discuss about that, which is Schottky effect, which is that let us define the potential energy of an electron far away from the metal surface as zero. Repeat. Let us define the potential energy of an electron far away from the metal surface, that means this surface, as zero. As we approach the metal with the electron, the metal will become polarized and will exert an attractive force on the electron for distance x larger compared with the interatomic distance. The metal surface may be considered homogeneous and the attractive force is given by the well-known image force. For example, this is the metal surface. If the electrons are accumulated at the surface, so at the same distance at the metal side, there is a create a opposite charge at the same distance, opposite charge. Due to this charge, there is a force which is called image force, and this image force make this barrier, this is the barrier, make this barrier is lower. Then it is starting from here, maybe this portion is lower. This is denoted by del phi b. So this is called Schottky barrier, and this, due to the image force, this barrier is low down. Okay, so lowering of phi b due to image force is called Schottky effect. Repeat, lowering of phi b due to image force is called Schottky effect. So due to the Schottky effect, if the barrier is lower, that means we need very minimum forward bias to move electron from n side to the metal side. So electrons, that means currents flow very fast due to the Schottky effect. Okay, or there is a higher concentration of electron and there is a empty. Okay, so it's immediately drawn out from n side to the p side, metal side.